All right. So we got this one little piece to go on example, whatever it was, 6. Yeah. So remember the second derivative test from yesterday is a test for, gosh, I forgot. What is it for? Yeah. Local extrema. Local max, local mins, relative max, relative mins. So we have to have our critical value in our possession, and then we analyze the concavity at that x value by looking at the second derivative value there, right? And just to review, if at the critical value it's concave up, then we have a local min. And if at the critical value it's concave down, we have a local max. And of course, if we get 0, it's also a possible inflection value. The test doesn't work. We have to go back and test intervals. All right, so second derivative can be nice if it's easy to obtain the second derivative. And I said yesterday that when we have data, charts, where we can't generate our own values to the left and right of a number, the second derivative test uses information at that point. Oh, one more. I'm in his desk. Okay. Thank you, Mr. Bird. All right, so we reviewed the IVT, we reviewed the MVT, and so now we're on part D, the part that's actually relevant to the new material. Does the function f have a local max, a local min, or neither at x equals 2? Okay, so this is kind of important. When you're thrown an x value for consideration for anything, local max, local min, or an inflection value, and you haven't found it yourself by taking a derivative, setting an equals 0, or seeing where it's undefined, you have to first say that that is a critical value, okay? We have to say that it's a critical value. Good morning. Thank you. Leno's checking out sometime. Okay. So, is there a local max, a local min, and either at x equals 2? Well, let's come up to the chart. Here's the row for x equals 2. First, look in the f prime column. What's the value there? 0. Okay, so we have to say that. That's part of the evidence. You could say f prime of 2 equals 0, so x equals 2 is a critical value of f. All right, so make sure you say that first, because local maximums can only occur at critical values, just like possible or inflection values can only occur at PIVs. All right, so now that we know it's a possible local maximum, it would be great if we looked at the sign of the slope to the left and to the right. Well, to the left of 2, the only point we have is at -3, and it's a positive number. And to the right of 2, the only number we have information about is 5, and it's a negative number. Can we then conclude that there's a local max there? No, because -3 is pretty far away from 2, right? 5 is closer to 2, but it's still 3 units away. There could be a discontinuity between 2 and 5, or -3 and 2. There could be a couple more critical values, so we can't do the first derivative test there. And notice they're kind of baiting you into it. There are some students that will say, oh yeah, since f prime changes from positive to negative at x equals 2, f has a local max there. No. So we come over here and we look at the second derivative value at 2, and it's 4. So here's what we'll say. The second derivative at our critical value 2 equals 4. And then what's important about the fact that it's 4? Not that it's 4 actually, but that it's what? Greater than 0. Okay, so that's your justification. And that means concave up, that's positive. So again, I like to draw the little smile, and then I button the bottom of the lip there, and then I can say, so f has a local min. Does it say, it says at, okay, so we don't have to find the value, has a local minimum at x equals 2. If it asks you to find the actual local minimum value, it would be the function value there, it would be 2. Yes, Kevin? Right. What if the second derivative there was 0? Yeah. They wouldn't give you a question like that using the second derivative test. That's a very good point, because if it were 0, then the second derivative test is inconclusive. And then based upon this data, we would say something like there's not enough information to determine if it's a local max min or neither. I'm not saying that they won't give you that question, but they probably won't. they're going to make it conclusive. Now, of course, if we had the equation or we had the graph and we got a 0 for the second derivative, then we would have to go back and do the first derivative test. So, excellent question. Yeah. All right, so there it is, second derivative test. Very, very useful, uses information at the value, and the justification's a little bit easier too. It's all about the inequality and then the statement. Okay, any questions about second derivative test or concavity? All right, cool. Don't forget there's a donation box on the rolly cart there. We're calling that the sanitation station now, the rolly cart. That's where you can find your Clorox wipes, your pump sanitation, your Kleenexes. And I have little packages of Kleenexes, too, from home. If you feel like you're getting a runny nose on the go, help yourself to one of those little travel packs. Yeah. Guys, there's one there that used to be my daughter's from several years ago. It has the Bratz Girls on it. Remember the Bratz Girls? That's free for the taking. There's some in there. There's some Kleenexes in there that look like $100 bills. So you could take those and try, passing them off on the grind or something, as long as Joy's not working, because she could spot those pretty easily. So anyway, and then paper towels on the middle shelf. So yeah, there you go. Any other questions? I brought all my decorations from home. If you notice, there's like trash pinned to the board over there. I got an old package of Sour Patch Trolleys just because it says squiggles on it. That's why. Some student gave that to me because squiggles, right? So that's why that's there. The cookie that's next to it is a pie cookie. That's kind of ironic right there, right? A pie cookie. And it's only 12 years old. There's two pie cookies in there. There's one facing the board and the one that you can see. So I would be willing to give up the back cookie to anyone who would want it later, right? Eats anything. It's only 12 years old, but it's cute. And then I have an old package of bubble gum there, the carton for it, and someone's like, why do you have trash? And I'm like, that's not trash, because if you open the lid, there's actually a calculus problem on it. And when we get to partial fraction decomposition, we'll actually work the problem that's on the gum wrapper. The gum wrapper says the flavor in this gum lasts longer than it takes to work this calculus problem. And the point of that ad campaign is like the average person is never going to be able to work the integral, and therefore the gum flavor lasts forever. Ergo, you should buy our gum. They don't really plan on calculus students buying that type of gum because you're done with the integral in like 2 minutes and like, man, this gum lost its flavor already. It sucks, right? So anyway, yeah, there you go. Okay, so if you're wondering why the room looks a little different, that's why. Okay, sweet. Let's move on to the next one here. Sometimes we need to be able to answer questions regarding the function and its concavity from a graph of f prime, okay? This would be kind of like me giving you a velocity graph and then asking you about acceleration, kind of the same idea. So here's the graph of the derivative f prime of some continuous function f. So the most important thing to consider when you're given a graph, an equation, or a table of values is, what is it a graph, equation, a table of values of? This is a graph of f prime. It represents the slopes. The y values represents the slopes of f from 0 to 9 as shown below. Answer the following questions in complete sentences. On what open intervals is f decreasing? Okay. Well, the average person that's not paying attention says, oh, decreasing? That's when this graph is going downhill. That would be from 2 to 3 and 5 to 7. Is that right? No, because they didn't ask us where f prime is decreasing. They asked us where f is decreasing. So how are we going to use this graph? Well, f is decreasing, if you want to help yourself here, when its derivative, f prime, is what? Negative. That's less than 0. So now we really want to look at something entirely different. We want to know where this graph is negative. Where is it below the x-axis? Okay, and it did say open intervals. So I'm going to say for 0 to 1, union 6 to 8. Now, if it didn't say open intervals, but it just said an interval, you would probably want to include 0, wouldn't you? Because notice, what is the value of the derivative at 0? It's some negative number, like negative 3. whereas at 1, 6, and 8, it's 0, okay? So this one could get a bracket if it didn't specify open interval. All right, that's not too bad. That would be kind of like saying this is a velocity graph. When is the particle moving to the left? Or when is the particle moving downward? Kind of the same idea. At what value or values does f have a local max or a local min? Oh, okay. So f is going to have a local max or a local min at critical values, right? So just thinking what we're used to, that's where f prime equals 0 or where f prime equals d and e. Again, we have to identify the candidates. So that's this graph. Where is this graph equal to 0? At 1, 6, and 8, right? So underneath there, I'm going to put x equals 1, 6, and 8. And is this graph ever undefined from 0 to 9? No. So I'm just going to put under here none. All right, so by doing that, I've declared my 3 critical values. And now we need to determine if those critical values are local max mins or neither. And we can use either the first or the second derivative test. Now, when you have a graph of f prime, this is essentially better than a number line chart. Better than a number line chart, because not only do you already know the signs of f prime, but you have some relative values there. So let's look at 1. To the left, f prime is negative. I'll just draw a little negative sign. And then it crosses the x-axis, and now it's positive. So that's better than a number line chart. We don't have to plug in and get a negative and a positive. We just look at the graph. We can go, oh, it crosses from below to above. So that would be the location of the local what? Min. And then at 6, f prime changes from positive to negative. That's going to be a local max. And then at 8, it changes from negative to positive again. So yes, all 3 of them ended up being local extremas. If they weren't, it would bounce off the x-axis. It'd be like positive on both sides or negative. So notice that the 2 local mins we could throw together. Let's do that. That's at 1 and 8. So now we could say f has local mins at x equals 1 and x equals 8, because f prime, don't say it, don't even say the graph. You might think when you say the graph, it's the definite article, and there can only be one graph because they only gave it to you, but that's still vague in the eyes of College Board. Just say f prime. It's a lot faster, because f prime changes from negative to positive, not in France, but at x equals 1 and x equals 8. Okay? And then the other one, because it changes in a different way or a different manner, that's at 6. F has a local max at x equals 6, comma, because f prime changes from positive to negative. So this is your communication component, your writing component, essentially. Not just a math class. You're justifying, you're explaining, you're defending your position. All right, so that would be full credit right there. Could we do the second derivative test? We could, right? You'd have to kind of make a stronger argument because this is the graph of f prime. But notice at 1, the graph is concave what at 1? Is that 1 the part of the graph where it crosses the x-axis at 1? Is it part of a frown or smile? It's part of a frown. Yeah, it comes in kind of concave down up until about maybe right there. That's concave down. So if you wanted to, I wouldn't necessarily recommend this. It's more work. But you could say f has a local min at x equals 1, comma, since no, that wouldn't be right? I'm looking at the wrong thing. If this were the graph of f, I could say it's concave down. But that's where you're getting in trouble here. If this is f prime, the second derivative are the what's of this graph? Slopes, yeah, are the slopes of f prime. So we're not looking at the concavity. Well, that's too much. We're just looking at the increasing, decreasing nature. Okay. So you'd say then, since f prime is increasing at x equals 1 by oops, you'd probably want to say either so f double prime of 1 is greater than 0, and that would actually make it a what? Not a min, but a, oh, it'd make it a min. Yeah, it'd make it a min. Positive. Yeah, so see, that's a much harder argument. I wouldn't do that. If you're given the graph of f prime, it's a continuous function, just use the first derivative test. Okay, so second derivative test would work there, but a much more challenging argument. On what intervals is f concave up? Okay, we could do that. On what intervals is f concave up? Well, now again, we got to be careful. We can't just look at the concavity of this graph. And here's where you can kind of trigger yourself. If you were looking like I was originally at the wrong thing, this graph would be concave down on this interval, and then they would change from concave down to concave up right there. Is that point marked? Does it coincide with the grid? No, you're in no man's land there. And it's not going to necessarily be 2.5. It could be 2.4. So that's an indication that you're looking at it wrong. So again, if you want to make this blanket statement up there, that f prime are the slopes of f, or f double prime are the slopes of f prime, that's not a bad idea. So now this graph is concave up whenever this function is increasing. So that's from 0 to 2, and from 1 to 5, and from 7 to 9. Okay, so you can list it like that. Let's do it up here. I'll do x epsilon, 0 to 2, union 3 to 5, union 7 to 9. And you could say since, here's your justification, since f prime is increasing on these intervals. Now that kind of goes against what I said about always talking about a sign change, but there's really not signs changing. You could also say since the slopes of f prime are positive on this interval. That would also work. Since the slopes of f prime are positive on this interval. So it's just a matter of looking at it and knowing how to use it to answer the questions. State the inflection values of f. Justify. All right, well, let's see if we can go a little bit more quickly here. We need to know where, first of all, the second derivative is 0 or the second derivative is dne. Now, this is where making this statement that f prime is equal to the or f double prime is the slopes of f prime, saying that once is nice because you always have to relate what you're doing to what's given. And if you just say f double prime and they're giving you the graph of f prime, you haven't quite made the connection yet. So if you say it once, now we know it's kind of like a map legend, right? You know what the different dotted roads mean, railroad, county road, whatever, highway. So where are the slopes of this graph? 0. Yeah, 2, 3, 5, 7. And if you're doing it right, they should all be marked. The ones you need should be kind of easy to identify. 2, 3, 5, 7. And then, are the slopes of this graph ever undefined? Do we have any vertical tangents or sharp turns? No. So that would be none. Now, I'm not going to write all the sentences, but notice that we're going to have 2 of each. So you would say at 2 and at 5, there's inflection values since the slopes of f prime change from positive to negative. That's where you want to talk about the slopes of f prime. Don't just say f prime goes from increasing to decreasing. If it's ever a change in sign, talk about the sign change. So since the slopes of f prime go from positive to negative at x equals 2 and x equals 5, f also has inflection values at 3 and 7 since the slopes of f prime change from negative to positive at x equals 3 and x equals 7. Let's write that second one out. You would want to do both of them because they're different, right? So f has inflection values at x equals 3 and x equals 7, comma, since the slopes of f prime change or go from, I forgot what they were, 3 and 7, negative to positive. Go from negative to positive at x equals 3 and x equals 7. And then you can go ahead and say, and also at x equals blah, 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 whatever they were, 2 and 5, also at x equals 2 and x equals 5, comma, since, and then you would say it also, since the slopes of f prime change from positive to negative. Okay, so the sentences can get kind of long, but no, you should be kind of picking up on the general theme in this section and the previous section of how you're expected to write those justifications. Okay, and then here's a good one that we're going to kind of do a little bit more of in the next section. Assuming that f of 0 equals 0, sketch a possible graph of f, and then a follow-up question, is it possible to determine the x value where the function attains an absolute max or an absolute min? Now notice it just says max or min, but you assume that it means absolute or global. So if f of 0 equals 0, all right, so I'm going to get rid of all this. F of 0 equals 0. So we're kind of trying to go backwards now. Here is our starting point. That's f of 0 equals 0. I need to sketch a possible graph of f, and this is what's going to take a little bit of practice. So here's where knowing the sign of the first and second derivative on any given interval is going to help you, because all you have to do is draw these little arcs from left to right depending on the sign of the first and second derivative. Okay? So what are we going to be looking at? We're going to be looking at the y values. We're going to be looking at the y values because those are f prime values. Those are the slopes. That's going to tell us if we're going to draw it going up or down. And then we're going to look at the slopes of this graph. That's going to give us the concavity values. That's going to tell us if it's going to be concave up or down. So every time a y value or a slope changes of this graph, we have to reassess, okay? So let's practice. On the first interval from 0 to 1, I have negative y values, so the function is decreasing. And the slopes of this graph are positive. That means concave up, okay? So if you want to help yourself here, negative values means decreasing. Positive slope means concave up. So starting at 0, 0, I'm going to draw something decreasing concave up. Well, that's going to look like that. That's the only way to draw decreasing concave up. How low do you go? That's up to you, right? It varies. That's why it says draw a possible graph. You could draw it doing more like that, or you could draw it doing that, whatever, as long as it's decreasing concave up. Okay, so boom. Now, on the next interval, from 1 to 2, I have positive y values, so it's increasing. I have positive slope, so it's concave up. So now it's increasing concave up. Do we get back to the x-axis? That's up to you. You might be above the x-axis, you might be below like I am, or you might be on it. That's entirely up to you at this point. All right, on the next interval, from 2 to 3, we have positive y values, so it's increasing, but the slopes are negative, right? So it's concave down, increasing concave down. So increasing concave down looks something like that, up to there. So see what we're doing? We're kind of offsetting everything by 1. The y values are positive and the slopes are positive. So that's going to be increasing concave up on the next interval. Positive, positive. We'll just do it like that. Positive y values, positive slope. That's positive, positive. That's increasing concave up, increasing concave up. Boom. On the next interval from 5 to 6, we have positive, negative, right? Positive y values, negative slopes. Positive, negative means increasing concave down, which is going to look like that. How high do you go? Whatever. On the next interval, from 6 to 7, we have negative y values now and negative slopes. Negative, negative means decreasing concave down. Decreasing concave down. Up to about right there. The next interval here from 7 to 8, I have negative y values, positive slopes. Negative, positive is decreasing concave up like a cup. And then finally, from 8 to 9, I have positive y values, positive slope. Positive, positive is increasing concave up. Now, how high does it get? I don't know. Does it ever make it higher than what we had at 6? Probably not. But could it? Yes. It could. So let's do that. That's a possible graph of f. Let's label it. Okay, now the follow-up question. Is it possible from your graph to determine just the x values where the function f attains its absolute maximum or absolute minimum? Let's do the absolute minimum first. Is there any question where the absolute minimum occurs? Regardless of how you draw it, the absolute minimum is going to occur at x equals 1. Yeah, at x equals 1. And notice it doesn't ask you to justify. Usually you're not going to have to. I'll just say absolute min at x equals 1. Is it possible to determine conclusively where the absolute maximum would occur? I don't think so either. There's two possible candidates, right? It's going to either occur at the local maximum, which is at 6, but it could also just as easily have occurred where? At 9, the endpoint. It just so happens the way I drew it, I drew the right endpoint a little bit smaller. Now later on when we start looking at areas, we're going to be able to quantify how high it goes up and how far it comes down and how high it goes back up. Okay? But this is qualitative analysis, not quantitative analysis. And so there's no way to definitively say that the way we drew it is correct. So I would say no to the maximum. No way to determine the max location. All right, not enough information. It gets down to talking about how quickly or how steep the graph is and how high it goes on the y-axis to determine how fast it's going up and how fast it's going down. But it's still just a qualitative analysis, okay? So how do y'all feel about that? That's the first time we've done that, going backwards. Anytime the y values of the slopes change, you want to reassess, okay? Y values are the slopes. Slopes are the concavity. All right, we will be able to finish tomorrow. There's only one more left. We'll probably do this as a warm-up. I'll probably give you like 10 minutes at the start of class to do example 8. It's very similar to what we just did, and then we'll go over it. And we said we were quizzing tomorrow, right? I'd rather quiz. Let's just wait till we're done with this section. Let's just quiz on Friday. Or is that a bad day? Let's do it. Okay, we'll quiz tomorrow. Oh, excuse me, Christmas tree. We'll quiz tomorrow. We'll quiz tomorrow. Just a quick little easy quiz, like 300 for everybody. I know you're doing your work. And then we'll finish the notes and then possibly move right into the next section. So, yeah, quiz tomorrow.